Welcome to final exam review of Calculus 2. And we start by finding the radius of convergence and the interval of convergence of the following power series. So we have the sum as n starts from 0 to infinity of 5n squared x plus 5 power n. So to check or to find the radius of convergence and the interval of convergence, we use the root test for this case. And so we do limit as n tends to infinity of n root of the absolute value of 5n squared, then x plus 5 to the power of n, which can still be written as limit as n tends to infinity of 5n squared multiplied by x plus 5 to the power of n, then all these to the power of 1 over n. And this will simplify. I'm still finding the absolute terms of this. So at the end root, we cancel with an n. So we have limit as n tends to infinity, 5, 1 n will cancel, you get only 1 n. And then you get x plus 5 and the n will cancel because of the n root. And then limit as n approaches infinity of 5 to the power of n and then x plus 5. So as n grows, then we find that the part that depends on n will become very huge. And this will be the solution. If you check that this will become infinity if x is not equals to minus 5. Because if x was equals to 5, if x was equals to minus 5, then you get that the whole real answer becomes 0. And that tells us that this series converges only if x equals to minus 5. Otherwise, if x is not equal to minus 5, this thing does not exist or diverges. And that, for find the radius of convergence, there's a simple formula here. We just take 1 divided by L. And L, for this question, when you find the L here, because n was growing, then the limit here is infinity. So 1 over infinity, which is equals to 0. So this is now radius of convergence. So if a radius of convergence is equals to 0, and this series converges only if x equals to minus 5, then that means that the interval of convergence here, it's a singleton, and I'm writing it like that, minus 5. Second question, we will use the ratio test. That because we can simplify the denominator easily, and that is limit as n tends to infinity of the term n plus 1 term in absolute form divided by absolute form of n term, and then this becomes limit as n tends to infinity. So whatever is given is this term here, we call it nth term. So we are finding n plus 1. So x minus 3, where you have n, you put n plus 1, divide by n plus 1. Then the whole of this you divide by the nth term, which was the original term, divided by n. So this will become limit as n tends to infinity, x minus 3 to the power of n plus 1 divided by n plus 1. Then you multiply by the reciprocal of this, that's n, x minus 3 to the power of n. So writing it in a more simplified way, we have limit as n tends to infinity, x minus 3 can be split into 2 to have power n, and another one to have power 1. Then I'm multiplying this by n. Then I'm dividing all these by n plus 1. Don't forget the absolute term, x minus 3 to the power of n. So this and this will cancel, and you'll be left with limit as n tends to infinity of n, it's left, over n plus 1, and then x minus 3. So we observe that x minus 3 doesn't have an n. So as n becomes bigger and bigger, we find that n over n plus 1 is that it's this one, the limit. We can write this one. You can factor out x minus 3, and then you find limit as n tends to infinity of n over n plus 1. So, and by now we know how to find the limit of this one. So we just get interested with the highest power of n, and that is n over n in the numerator and denominator. So we get that the limit here equals to 1. And that means that our answer equals to x minus 3. So for this to converge, x minus 3 has to be less than 1 for checking for convergent. So it has to be less than 1. So we can write this in form of minus 1 less than x minus 3 less than 1. So that's how we write this. And then solving for x, we have that x is less than 2 and x greater than 2 and less than 4. So those are first the interval. This should be closer to giving us our answer of the interval convergent, but we need to check the endpoints to check whether indeed the endpoints are in the interval. So check the endpoints. So checking the endpoints, we start by checking 2. So unchecking is by substituting x with 2 in the original series. So limit as n tends to infinity. Now 2 minus 3. So put 2 minus 3. So in the series, so let me do that part here. So in this series, anyway, so let's check at 2. Check endpoint. So x equals to 2. If we check this one, we have the original series or sum. N starts from 1 to infinity. So 2 minus 3, it's minus 1 to the power of n divided by n. And this, if you check the test of this series, because it has a minus 1, we use the alternating series test. And we observe that if we let Bn to be 1 over n, then Bn plus 1 should be less than Bn. If you check, and then also since this one is alternating, and this one is less than none, then we find the limit as n tends to infinity of Bn of 1 over n, and you find that this one is equals to 0. So this one converges, and that means that we will include 2. So I'm putting a line below the strict inequality to say that 2 is included. And then let's check at x equals to 4. So again, we have the sum in the original series starts from 1 to infinity. 4 minus 3 will be 1. So 1 power n is just 1 over n. So we know that this series is called, it's a p series or a harmonic series, and this diverges. That means that in our interval, we won't include 4. So that means that the sequence converges and this interval. So I'm putting 2 in the square bracket and 4 in the open parenthesis. So this is our interval of convergence. So for the radius of convergence, R, always remember, is equals to 1 over L. Now, since we are not, we found L here as 1, so R equals 1 over 1, which is equals to 1. So let me clear that part. I move to the next one. So for the third one, we will use again the ratio test. So limit as n tends to infinity, use the limit. So let me stop this. So let's use limit as n tends to infinity of n plus 1 factorials, then multiply by x n plus 1, and then after terms, that's the a n plus 1 divided by a n, that's n factorial, x to the power of n. So this is the same as we reduce the factorial so that they can cancel with n factorial in the denominator. We have n plus 1 multiplied by n factorial. Then x power n multiplied by x power 1. This divided by n factorial x to the power of n. And I'm looking using the absolute because I want to get positive numbers. So n factorial cancel with n factorial. X to the n, we can cancel with x to the n. And this will be left as a limit as n tends to infinity of n plus 1 multiplied by, we put this, x. So as we find the limit, we find that this does not depend with n, so I can factor that out. Limit as n tends to infinity, n plus 1. And as n grows, this limit here becomes infinity. And that means we can be able to find the radius of convergence. As we know, it's r equals to 1 over L. That's 1 over that big number, which is equals to 0. And let's find the interval convergence. So we know something here that x minus c should always be less than r. And in this case, r should always be less than 1 for it to converge. So this side, we have our r as 0, less than. And in our question, we have x. So that means that our center is 0 and radius is 0. So if the center is 0 and radius is 0, so if you have to draw like a number line, we have our center of convergence is there, and the radius is 0. That means that this thing has the interval of convergence as a singleton 0. Finally, the last question. Is we find the limit as n approaches infinity. Again, we use the ratio test. So we have n plus 1, x plus 2 to the power of n plus 1, absolute form, divided by 3, n plus 1 plus 1, that is 3n plus 2. Then because I'm dividing by the original term, so I multiply by the reciprocal of it, 3n plus 1 divided by n, x plus 2 to the power of n. So this is absolute, and this one is absolute. So we have the limit as n tends to infinity, and so we have n plus 1 in the numerator, multiplied by, I can split this one as x plus 2 to the power of n, with another one x plus 2 to the power of 1, multiplied by 3 n, and then I'm having a 3 to the power of 1. I can split again that one. Then I divide now by the denominator, which is 3 to the power of n, multiplied by 3 to the power of 2, multiplied by n, multiplied by x plus 2 to the power of n. And then all these in absolute symbol. So this we cancel with that one. 3 to the power of n cancel 3 to the power of n. I'm having 3 copies, 1 copy of 3 in the numerator and 2 copies of 3 in the denominator. So 1 copy will cancel with another 1 copy here, but only 3 to the power of 1. And that means that to clean it up, I'll have limit as n tends to infinity, n plus 1 divided by n. And then in the numerator, multiplying by x plus 2. Absolute terms, denominator we have a 3. So observe that I can factor out, this is the same as, I can factor out what does not depend on n, x plus 2 over 3, and then limit as n tends to infinity of n plus 1 divided by n. So, and we find that as n gets bigger and bigger, the answer for the limit is equals to 1. Now we know. And for this series to converge, then x plus 2 over 3 has to be less than 1. That's the ratio test we know. That for it to be converge absolutely, or to converge, it has to be less than 1. And that means that if I was write this one in this form, I will have minus 1 less than x plus 2 and x plus 2 less than 1. And I'm having over 3 here. So I multiply by 3 all the sides. I have minus 3 less than x plus 2 less than 3. And then that means that x is between minus 5 and 1. So we need to check the endpoints. So check the endpoints. So we check minus 5 to see whether it's in the interval, or to check and check minus and check 1. So let me check here at this point, check x equals to minus 5. So, and I'm checking it in substituting x in the original series. So I'm having summation as n starts from 1 to infinity, n x is minus 5. So minus 5 plus 2, that's minus 3 to the power of n divided by 3 to the power of n plus 1. So I can add 3 to the power of n, then I can factor out 1 over 3. And then this is the same as 1 over 3 sum as n starts from 1 to infinity, n minus 3 power n divided by 3 to the power of n. Since they have the same power, I can just multiply minus 3 times that. That's minus 3 over 3 to the power of n, which this becomes a third. The sum as n starts from 1 to infinity, n to the power, and then minus 1 to the power of n. So this series Yes, it's alternating. We can see it's alternating, but this is the Bn term is not decreasing. So because Bn plus 1, you can say n plus 1. So it's alternates. So it decreases, but the limit is not equals to 0. So this one, we're using the alternating series test, this one diverges. So, and again, to check using the alternating series test, you check whether the Bn plus 1 is less than Bn, and then you check whether the limit as n tends to infinity of the nth term is equals to 0. And you can check the limit is not equals to 0 for this case. So that means that that point x equals minus 5 should not be included. And let's check x equals to 1. So again, we have the sum as n starts from 1 to infinity, n, 1 plus 2, that's 3. So having 3 to the power of n, and then I'm dividing here by 3 to the power of n plus 1. So it's 3n, then I can factor out 1 over 3. And this will cancel, and I will have a third, the sum, as n starts from 1 to infinity, and then n. Again, this one diverges. That means that our interval convergent, it's open parenthesis, or the way it's like in this form in terms of interval notation. That's the end of the video.